All right, so we'll get started again. And there was a question before the break concerning what happens if the potential is time dependent. And well, we made one assumption here, that we are dealing with a conservative system. So if the potential energy has an explicit time dependence, what happens with the system's energy then? So you say that if the potential energy in the system has an explicit time dependence, what happens with the conservation of energy? What we're actually going to show in a couple of lectures' time is that if the partial derivative of the Lagrange function with respect to time is non-zero, then we actually have broken energy conservation. Energy is no longer a conserved quantity. But in general, you can still write Lagrange equations in the same form. This can be shown. So, in fact, to give an example of this, we're going to move on to a situation where the potential is allowed to depend not only on the spatial coordinates q, but also the sort of generalized velocities q dot. Before doing so, I would just like to point out that sort of what is the purpose of writing down Lagrange equations? Because we have Newton's second law, right? We have the force is equal to the time derivative of momentum. This is a vectorial equation. What we've accomplished here is, for one thing, we have removed all the constraints in the system, and we've reduced the problem to a set of scalar equations. Right? There's no vector quantity here. So we reduced the problem from a vectorial system of equations, namely Newton's law, down to a set of scalar equations without any additional constraints in the system. All these generalized coordinates q are independent on each other. So this is a major simplification. So let me write this. We've eliminated all the forces stemming from constraints in the system. In addition, we've ended up with a set of scalar equations in contrast to Newton's second law. These are easier to deal with. So let's now have a look at what happens if you consider more general types of potentials, namely velocity-dependent potentials. And we'll start a bit backwards, and I'll give you the result right away, and then we'll derive this. Turns out that if the potentials are velocity dependent, then we can write Lagrange's equations in exactly the same form. If the generalized force can be written like this. So the first term here is the same as we had when we derived Lagrange's equations for a conservative system. This is the same form as the force in a conservative system. It's just a gradient of some potential. But if the generalized force has an additional term, like this, then Lagrange's equations remain invariant in form. Where the Lagrange function is now t minus u. So we'll show this now. So the assumption is that the potential is now dependent both on position and velocity, q dot. And the example that we'll study in detail is that of an electromagnetic field. Or potential. And this is important because it shows you that Lagrange's equations can be used not only to analyze mechanical systems, but also, in fact, systems where you deal with the electromagnetic force. The Lorentz force, the force acting on a charged particle moving in an electric and a magnetic field, can be written like this. So you have a contribution here from the electric field, and in addition a cross product here between V and B. Does this look familiar? You've seen it before? Yeah. Now, from Maxwell's equations, which are the equations that determine how the electromagnetic potentials are related to the fields, we can show that the electric field and the magnetic field can always be written in this form, expressed by means of a scalar potential phi and a vector potential A. So if you write the electric and the magnetic field in this form, they will automatically satisfy Maxwell's equations. So phi is a scalar field, A is a vector. we insert this into the Lorentz force. And get this. Now, before moving on with this example of the electromagnetic potential, this is a suitable place to have a small intermission where we introduce something known as the Levi-Civita tensor. And this will be a useful tool for you when doing various types of analytical calculations in this course. Let's assume that we're dealing with Cartesian coordinates. As opposed to, for instance, polar or spherical coordinates. So x, y, z. Then, when dealing with this Levi-Civita tensor, it is useful to introduce a sum convention. And this is just a way of writing things, which makes it easier to keep track of. So the sum convention is expressed as follows. If you have two vectors, A and B, and you take the dot product between these vectors, then you get A1, B1 plus A2, B2 plus A3, B3. If A has three components, A1, A2, A3. So we can write this quite compactly as AI, BI. So this means that whenever you see repeated indices without any sum, then this implicitly means that you have a sum convention. This means that you should sum over the index I. And one has to be a little bit careful because sometimes this could also, for instance, mean just the ith component of A multiplied with the ith component of B without any sum, right? So one just has to be careful and check both sides of the equation, what kind of convention or notation is used. If we wanted to be 100% sure that this wouldn't be misunderstood, we could add sum over I, right? But as we will see, when using this Levi-Civita tensor to simplify the calculation of, for instance, complicated cross products between vectors, then you would often end up with sums over many indices. So you would have to write sum over I, j, k, l, m, n, for instance. So then it's just more practical to omit the summation sign and just write a, I, b, I. So in this case, it's clear that this means sum over I, because we have no I dependence here. So whenever you see repeated indices, I, just think for a while, does this mean that we're dealing with a sum convention? Because it could be. And similarly, we can write the following. So the gradient of the gradient operator does with A would then be the partial derivative of AI with respect to xi. So repeated indices again, this means a sum. And we could also write this as AI, comma I. This means that you derive the ith component of A with respect to the ith x component. So this is just some notation that you will encounter, not only in this course, but also later if you take more advanced theoretical physics courses. So it's good to be aware of. Okay. So now on to the actual Levi-Civita tensor. What is that? It is an anti-symmetrical quantity in all the indices I, j, and k. It changes sign if you exchange two indices. And it's equal to 0 if two indices are equal. So epsilon ijk is equal to +1 when the indices I, j, and k are cyclic. And by this I mean that they appear in order. So for instance, epsilon 1, 2, 3 is equal to +1. If I now exchange two of the indices, so epsilon 3, 2, 1, 3, 2 is equal to -1. And note that by cyclic, we can also have, for instance, epsilon 2, 3, 1. You just count, you start, when you reach the final index, you go back to the start. So here we have 1, 2, 3. Okay, this is cyclic. So we have 2, 3, 1, 2, 3. So 1, 2, 3. It's still cyclic. You see that we obtained the 2, 3, 1 combination by exchanging two of the indices. We exchanged both 3 and 2 and 2 and 1. So it's still +1. Okay? So if you just remember this, epsilon 1, 2, 3 is equal to 1, then you can find the value of any other combination of the indices just by remembering that if you exchange two indices, you get a sign change. So if you exchange two indices twice, you get back the same sign. The reason I've introduced this Levi-Civita tensor is because it's useful to have when you want to calculate cross products of vector in particular. So if you have that the vector A is the cross product between vector B and C, then the Levi-Civita tensor is defined in such a way that that the ith component of A is given as epsilon ijk multiplied with bj and ck. So note here that we have repeated indices on the right-hand side. We have jj and kk, but we only have I at one location here and at one location here. So what this really means is that we have a sum over j and k due to this sum convention that if you have repeated indices, then you have to sum over those indices. And let me also write down a useful relation which can be mathematically proven for the Levi-Civita tensor. So here we have a summation over I, because we have repeated indices I, and therefore there's no I dependence here. And the delta function here is the Kroneker's delta function. Which is equal to 1 if these indices are the same, but it's 0 otherwise. Okay, so let's just do a quick example. Say you want to calculate this scalar product between two cross products. This would be a real pain to do, right? You can write down the determinants or, well, I don't know how you're accustomed to calculating these cross products, but let me show you an alternative way using this Levi-Civita tensor. So this is equal to this, using the sum convention with repeated indices. And here I just use this definition over there. So the ith component of a cross product can be written like this. And note that all of these quantities are now scalar quantities, so we can move them around just as we want. They commute. So it means that I can take, for instance, this epsilon and move it over here and use this relation. So now we know that the Kronecker delta function only gives a finite contribution if the indices are equal. If they're unequal, then it's 0. So from the first term here, we only get a contribution when j is equal to L. So we get AL, CL. This is A dot C. And we only get a contribution when k is equal to M. So we get BM, DM here. And then similarly for the last term here. So we've managed to rewrite this scalar product between cross products to a sum of scalar products, which is much easier to evaluate. So this is just one way you can use the Levi-Civita tensor to manipulate expressions containing vector operations. All right, so back to the electromagnetic potential. Using the sum convention, I can rewrite this like this. Inserting this into the expression for the Lorentz force, we get this. So these two first terms stem from the electric field, and this last term comes from the contribution of the magnetic field. Now, we observe here that we can write this, because we have a sum over Vj, Aj. So this is just a scalar product between the velocity vector and the magnetic vector potential A. And the reason for why I can take this derivation, partial derivation operator, and move it to the front is because V, the velocity, is independent on position. So this operator commutes with the velocity. It only acts on this magnetic vector potential. Moreover, I use the following product rule or chain rule for derivation. So the total time derivative of AI is equal to the partial time derivative plus the partial derivative of position with respect to time multiplied with AI, like this. So this is just a chain rule for derivation. If I now combine this equation and this property and insert them into our expression for the Lorentz force, we first have this term, which we have rewritten like this. And then we combine this with the final term to form the total time derivative according to this equation. So we're getting close now to the final result, because we can write this equation like this. This term is just these two terms. And here I've just rewritten this total time derivative in a slightly different way. By deriving with velocity, we get back the vector potential. Now, these potentials, phi and A, that we introduced in order to express the electric field and magnetic field, they depend on position and time. And so it means that I can actually add a phi term here inside this parenthesis if I want, because deriving it with respect to velocity would give 0. So if I now add minus phi here, I can write the total Lorentz force like this, where I've introduced the quantity u is q phi minus q ab. And if you recall the starting point of our investigation for velocity-dependent potentials, you see that this is exactly the form that we require the force to have in order to write the Lagrange equations in the same form as before. We showed that if the generalized force can be written like this, Lagrange's equations would remain the same if we define L is T minus U. So in other words, let me write it over here. So the Lagrange function for a charged particle moving in an electromagnetic field is the following. So you see now that U no longer represents the actual potential energy of the system because of this extra term here. For a conservative system, we will get the Lagrange function is equal to T minus V, where V is the actual potential energy. For this case, the electromagnetic field, we get T minus U, where U now is a velocity-dependent potential, but it does not represent the actual potential energy. This term here is not related to potential energy, whereas this one is. Okay. The final thing we'll do in this lecture is to say something about how friction can be taken into account. Because when we derived Lagrange's equations using D Alembert's principle, we stated that frictional forces could not be included when making this assumption that the forces stemming from constraints would be perpendicular to the virtual displacement vector. So it means we have to take into account friction separately. And what you can show is that if you assume a holonomic system, then you can always write Lagrange's equations in the following form. Where now L contains the potential which originates from forces that are conservative, whereas Qi contains the contribution from all other forces, including friction, which are not conservative. So Qi represents the forces that cannot be derived from any potential, such as friction. And frictional forces are typically proportional to the velocity. Typically. And you might be familiar with this. For instance, if you consider if you just consider Newton's second law in one dimension, say along the x-axis, and you have some, say, oscillating system where you have a spring constant k. Then the solution for this system is something like that. In general, superposition. Square root in addition. So it just corresponds to sort of an oscillating solution. You can combine these to get cosine or sine or something like this. Yeah, possibly should be an I here, sorry. To get the minus sign. Now, if you include friction, you can typically model this by adding a term to Newton's second law, where you have lambda x dot. So it's lambda multiplied with velocity, where lambda is a constant characterizing the strength of the friction. And what happens here is that solution, I really messed up here, sorry, it should be time. You typically get something like this. You get an oscillating part, but you also get a damping term, an exponentially damped term. Again, should be time. Due to this extra frictional term in the equation. I don't know, have you seen these types of equations, for instance, in Mekanikk 3, which you might have had? Yeah. So friction is typically modeled by a velocity-dependent term, and it gives rise to an exponential damping in the system, typically. It's possible to introduce kind of an analogy to describe a frictional force with the force in a conservative system. So if we accept this ansatz, if you will, for the frictional force, that it's some constant multiplied with velocity, then the x component of the frictional force is given as the partial derivative with respect to the velocity in the x direction of this quantity here. So this is kind of analogous to the force in a conservative system where you have the gradient, the positional derivative operator with respect to some potential here. So in 3 dimensions, we can generalize this to writing the frictional force as the gradient with respect to velocity. So this means gradient operator where you derive with respect to velocity instead of position of some function curly f here. And this curly f is a commonly used form for this curly f is Rayleigh's dissipation function, which looks like this. Precisely so that you get a force which is proportional to the velocity. Okay, so I guess we have to finish up next time for friction.